For part 7 of our videos on convergence tests to determine whether infinite series converge or diverge, we're going to look at something called the integral test. And before we do that, I want to take a quick look at the tests that were covered in the previous videos and understand how these are all interconnected. So in part 1, we did an overview of infinite series and what they meant and how we were going to use them. And then in part 2, we looked at infinite geometric series and how you can determine using information from geometric sequences and series from earlier in the course. How you could use those to determine whether a series converges or diverges. Then in part 3, we looked at the divergence test, which basically kicked us onto a different side of our flow chart. So the first thing you always check is you check to see if a series diverges. And if it diverges, you're done. If it converges, then we get to all these ones down below. So that's always one of the first ones you want to check to see if a series diverges. And if you need to check that out, you check out video 3. Video 4, we looked at arguably one of the most used ones, which is the PSeries test. There are 2 other tests we'll talk about below that are just as important. I say my big 3, we'll get to in a second here. Video 5 talked about comparison test. Video 6 then talked about limit comparison test, and I think that is number 2 of the big ones. So P-series and limit comparison test are 2 of your 3 big ones. So in this video, part 7, we're going to look at something called the integral test. Now, if P-series and limit comparison test are the most used, I would argue that integral test is the least used. It does have its uses in very specific forms, but overall, there are usually better tests to use that are easier to manage. And so we're going to look at it anyways, though, because there are some situations where it can be useful. And so the integral test for a series basically says that if you have a series, and specifically, we're going to look at whatever the series is, it's going to be infinite. We're going to look at the rule for it. So whatever the rule is for this, we're going to look at that. And given the fact that it is a decreasing function, so whatever this guy is, we have already discussed or figured out that it is decreasing, meaning you don't want a function that's increasing, meaning that if you were to take values in the series, they keep getting larger and larger. And then if you keep adding those, clearly the sum is going to approach infinity. So that's not really anything we need to look at. The second thing is we want it to be positive, similar to the other functions we've been dealing with in these geometric or whatever P-series tests we've been looking at. We're always looking at ones that are strictly in quadrant 1. So we're not venturing into quadrants 2 and 3 because we're not going to deal with negative terms. Negative, and by negative, I mean, if I ask you the second term or the third term, I'm never going to ask you for the negative 4th term. A term doesn't exist. And also, we have not ventured into any that are down in quadrant 4, which would be if you have functions that give you values in a series that will be negative. We'll actually talk about that in the next test, which is something called the alternating series test. So basically what the integral test says is take whatever your rule is, evaluate the integral, and the lower boundary here is 1. That boundary of 1 corresponds to whatever the lower boundary of your series is. So if your series starts at a value of 2, then this value down here becomes 2. If this is a 4, this becomes a 4. Whatever the lower the starting value of your series is, that's the value we're going to use here. And we're going to find that that really doesn't play a huge role in most of the problems we're going to do. But basically what the integral test says, that evaluate the integral, and if the integral converges, then your series converges. And we talk about an integral converging, that means when you evaluate the improper integral, we call this improper because it has an infinite upper boundary. So if this approaches some number, any number, we just don't want it to approach infinity, then we say that the integral converges. And for context, what did it mean to have an integral that converged? We said that if you have a graph that does something like this, so let's say it starts at k equals 1, and we look at integrals, integrals evaluate the area under a curve. And so what does it mean for an integral to converge? It means that the area under the curve models finite behavior. Now we know that a lot of the ones we dealt with in previous sections, this graph never actually touched the x-axis. So technically, if we look at that, this value or this area under the curve is infinite. Well, we found, though, that if this graph gets small enough, fast enough, that even though it doesn't have a boundary here on the right side, that the area under the curve does model finite behavior. So if the integral converges, the series converges. If the integral diverges, meaning it approaches infinity, then the series also diverges. So a good example of that is if we look at the P-series test and how we first approached the P-series test back when we did improper integrals, we looked at the rule for integrals and we found this rule that said if you evaluate an integral from 1 to infinity, and again, this value can change a little bit, but overall it doesn't have a huge impact on the integral itself. And we said that if it's in the form of 1 over x to the p, if p was larger than 1, we said p equals 1 was kind of like that cutoff. If p was larger than 1, we said the integral converged. And so the example of that was this particular integral, which is the integral from 1 to infinity of 1 over x. So we said the graph of that lies only in the first quadrant. It looks something like this. And we determined through proofs that 1 over x, so the function y equals 1 over x, did not get small enough fast enough for the area under the curve to model finite behavior. So how does that apply to series? Well, if this particular integral diverges based on the information I just said there, and we can prove it, but that's not the purpose of this video. So if this diverges, then we know the series using the same values. So from k equals 1 to infinity of 1 over k, which in case you guys do not recall, 1 plus 1/2 plus 1/3 is the harmonic series. And we know that the harmonic series does not converge. So if you keep adding 1 plus 1/2 plus 1/3 plus 1/4, that will approach infinity. So the values are getting smaller, but they're not getting small enough fast enough. We then kicked up to the next type of function, or the next integer exponent. We said that if it's 1 over x squared, and 1 over x squared's graph looks very similar, but it has some shape differences, it gets closer to the x-axis faster, and we found that 1 over x squared does actually converge. And the reason for that was, since 1 over x squared, if we added those together using a series, the first term would still be 1, but then the second term would be 1 over k squared, so it's 1/4, plus 1 over 3 squared, so 1/9, plus 1/16. So the fact that these values are getting smaller much, much quicker than these, we determined that 1 over x squared actually converged. And so because of that, we know that the series from k equals 1 to infinity of 1 over k squared also converges. And so integrals are really the basis for P-series. They're very interconnected. So if you ever use the P-series test, know that a lot of that is based in the rules that you learn for integrals. So how do we actually do that? So here's a summary for integral tests. So it says whatever your rule is, so we have f of k, says just evaluate the integral. If the integral converges, then the series converges. And I didn't list this over here, but obviously the other side of that coin is if the series diverges, then so does the series. So the first one I give you here, and again, the integral test is not super useful for a lot of series because there are other ways to test these. In fact, the one I've got right here, k over k squared plus 9, I'm going to actually show you after I do the integral test that there was a better way to do this that was a little more efficient. Okay, so it says use the integral test to determine whether this particular series converges or diverges. So what we do is we evaluate the integral. So it's the integral from 4 to infinity. And the reason I chose 4 is because my series is starting at 4. So these values, the lower and the upper boundary for my series, become the upper and lower boundary for my integral. That's the integral so the integral from 4 to infinity of k over k squared plus 9 dk. Notice this is not dx because k is now my variable. And in case you do not recall, when we evaluate improper integrals, the first step we do, infinity is not a number. So if you integrate something and then you have to plug in numbers, infinity is not a number, so we need a way around that. And the way we did that was we used limits. And so we have the limit as b approaches infinity of, and then we simply rewrite the integral from 4 to b instead of 4 to infinity of k over k squared plus 9 dk. So the rest of it does not change. We essentially just added this component and this component, which will allow us to use limits to evaluate the integral after we integrate it to plug in numbers because you can't use infinity as a number. Okay, so from here, I need to integrate k over k squared plus 9. To do that, I actually have to use u substitution. because it is not in any form that I can handle right now. Luckily, the u substitution of this is fairly straightforward. We're going to make u equal to k squared plus 9, which is the denominator. Du then is just the derivative of k squared plus 9. So the derivative would be 2k dk. And then we'd like to substitute these values in here to essentially kick out all the k's. The problem here is I've got k and dk, which are here and here. I've got k squared plus 9, but now I've got this extra 2 that's floating around in the substitution. So to get rid of that, we're actually going to multiply both sides of this particular integral by 1/2. So we get 1/2 du equals k times dk. And there are our substitutions. And so now we leave this, the limit as b approaches infinity of the integral from 4 to b. And now we do our substitutions. The k dk that's on top becomes 1/2 du. And since 1/2 is a constant, we can put that out in front of our integral. There's our du. And then you're left with k squared plus 9, but it's in the denominator of the fraction. So it's 1 over k squared plus 9, which becomes 1 over u. Now we integrate. And so we do the limit as b approaches infinity. The integral of 1 over u is one of our most common integrals. That is the natural log. So we do the natural log of the absolute value of u. And now this started off as an improper integral. Now with using limits, it's acting like a definite integral. So once we integrate, there is no plus c. We're evaluating it from 4 to b. And now this is the part you have to be really careful of when you integrate, if you haven't done these in a while, is if you do any u substitutions, you do not plug the b and the 4 in for u. U actually represents k squared plus 9. So before you plug any values in, you have to substitute that value for u back into this. And so I'm going to go ahead and pull the u out. You are allowed to pull any constants out in front. So we have the natural log of the absolute value of k squared plus 9, which is what we had for u, from 4 to b. And now we plug the values in. So we have the limit as b approaches infinity of 1/2. And so when I plug in b into this parentheses, I get the natural log of b squared plus 9. And I'm going to go ahead and write this as using parentheses as opposed to absolute value, because based on our integral here and our series, we're dealing with positive values from 4 to infinity. So here, if I take a positive value and square it, and then I add 9, it's not going to give me any negative values. So if you still want to keep the absolute value in there, that's fine. It doesn't really have an effect. So the natural log of b squared plus 9 minus the natural log of 4 plugged in. So 4 squared is 16 plus 9 is 25. And so now we can finally evaluate our limit here. And this was the whole purpose of doing the limit as b approaches infinity. If I look at this particular value, and let's put a box around it, the natural log of b squared plus 9, as b approaches infinity, b squared plus 9 gets infinitely larger, which means the natural log also gets infinitely larger. If you recall, a natural log graph looks a little something like this. And so even though it does get slower, or gets larger quite a bit slower than something like an exponential, it still does eventually approach infinity. So this particular value, if I say, what is the limit as b approaches infinity, it approaches infinity. Excuse me. And so now I have infinity minus this constant here, which is irrelevant. This tells me that this particular integral approaches infinity, therefore it diverges. And using the integral test, it says if the integral diverges, then that tells us that the original series also diverges. So in this particular example, this series from the sum from k equals 4 to infinity of k over k squared plus 9 diverges, and our reason is the integral test. So now looking at all that, that seemed a little excessive. We had to use improper integrals. We had to use u substitution. It seems like a lot of work. So for this particular value or this particular series, there's probably a more efficient way to do it. And that more efficient way was probably the previous test in video 6, which was the limit comparison test. So I'm going to go ahead and do that below here. But if you're good on the integral test, you can stop watching. And so basically the way the integral test worked, it had a lot of issues. It just took a while. What I'm going to do now is I'm going to write the series from k equals 4 to infinity of k over k squared plus 9 and show you how the limit comparison test could probably work a little better. Now, normally when we do these, we try the comparison test. And I always ask you guys to look at the leading terms or the highest power term on the numerator and in the denominator, and looking at k over k squared, this series looks like it's acting like 1 over k. Now, we can't just say that it diverges because it's 1 over k. We have to do a little bit more work. But the idea here is I know that this series is really acting like 1 over k. Now, the problem with doing this is what if we try to do just the comparison test? And that's from video 5. Is we try to write an inequality that compares something to k over k squared plus 9. And the easiest way to manipulate this would be to get rid of the 9. So if I subtract 9 from the denominator, I get k over k squared. And so what I really did was I subtracted 9. So I made the denominator smaller, which made the fraction bigger. And so I've got k over k squared, and that actually simplifies to 1 over k. So this inequality, if we ignore this, is true. We have k over k squared plus 9 is less than or equal to 1 over k. The problem with this is 1 over k is the series that's on top. We went over this in previous videos. If you've got two series that are both doing adding terms and approaching whatever they're approaching, if the series on top diverges, then that means it approaches infinity. And unfortunately, if the top series diverges, that doesn't really tell us anything about the bottom series. So the fact that this diverges, and I know this diverges because of the PSeries test. So it's 1 over k to the first power, and since this is not larger than 1, I know it diverges. Unfortunately, that doesn't tell me anything about this guy. So we're left with the situation where the comparison test did not work, and so we were left with the limit comparison test. And by the way, if I took this and said, well, can't I just flip this around and write it as this? So 1 over k is less than or equal to k squared plus 9. Then if you can show this diverges, you can show this diverges, but unfortunately this inequality is not true. So you're left with a situation where comparison test doesn't work, but with limit comparison test, we can still use this 1 over k. And I'll go through a little more quickly because this is more about the integral test. We look at the limit as k approaches infinity of these two series. And with limit comparison test, you always want to put the more complicated of the two that you have in the denominator. So if you have not watched video 6, this is probably not going to make a lot of sense. So part 6 goes over in more detail the limit comparison test. But once we simplify this, and let's get him out of here because he's kind of in the way. And so we simplify, we have a fraction of our fraction, which simplifies to k squared plus 9 over k squared, which simplifies even further into 1 plus 9 over k squared. And now the limit as k approaches infinity, since k is in the denominator here, the denominator getting infinitely larger means this part approaches 0, therefore this approaches 1. And with limit comparison test, we want this value to be larger than 1. Basically, we want this number to be anything other than 0 or infinity. And so since this value is 1, which is greater than 0, we now know that these two series, this guy and this guy, work together. That's how the limit comparison test works. And so now going back to this, if I have the series 1 over k, I know that diverges, and the reason is the PSeries test. Therefore, our series, which is k over k squared plus 9, also diverges. And our reason was the limit comparison test. So this video is more about the integral test, but it was basically showing you that when you do integral test, a lot of times there are other tests, in this particular example, limit comparison tests, that are a little more efficient, and it saves you the trouble of having to go through all the improper integrals and the u substitutions. So hopefully that was beneficial. And in our next series, our next video, we'll take a look at the alternating series test. What happens if you start getting negative terms?